Hi everyone, my name is Neha and this is the 8th lecture on Introduction to Automation. In this lecture, we are going to learn about semiconductor force sensors and low force sensors. Semiconductor force sensors, they use this piezoresistive effect of silicon, and these units they change resistance when force is applied, and they are 25 to 100 times more sensitive when compared with the bonded wire strain gauge. Here you see FSG series semiconductor force sensors, and in this a single strip of silicon material is used and that is bonded to the structure. So what happens in the semiconductor force sensor? When the structure stretches due to the application of the force, then the silicon present inside the force sensor, it will be elongated and the resistance from end to end increases, and this change in the resistance is non-linear, and this change in resistance can be recorded in terms of voltages or any other electrical parameters. Now let's see FSG series features and benefits. It has low repeatability error of 0.2% span, low linearity error of 0.5% span, resolution to 0.0098 Newton, fast response time, low power consumption, high electrostatic discharge resistance of 8 kilovolts, and extremely low deflection. So these were some of the features and benefits of using FSG series semiconductor force sensor. Now let's move on to the low force sensors. These are used for application where low force is required. For example, imagine the sensitivity required for a robot gripper when it is required to hold the water glass without slipping and without crushing it. So in that situation, you might need to use low force sensors. And in the strain gauge, if you use the strain gauge, then it can also measure the low force. For that, the construction will have to be a little bit different. So if you're using the strain gauge, then you need to mount it on a elastic substrate like rubber. Then a small force will cause a significant deflection and change in the resistance. And another solution for a low force sensor would be to construct with a spring and a linear potentiometer. So as you see here, there is a spring here and force is applied from here, and this is a linear potentiometer. So as the force applied, the position of this linear pot will change, and corresponding to that the resistance will change, and that change in resistance can be obtained in terms of electrical parameters. A very low force tactile sensor is also an example of a low force sensors where the sensor can be made using the conductive foam, and the conductive foam is basically a soft foam rubber saturated with the small carbon particles, as you can see over here. And its top membrane is of rubber, and here you see the carbon granules. So what will happen when the foam is squeezed, or when the foam is put with some pressure, then the carbon particles present inside, they are pushed together and the resistance of the material will fall, and this resistance will be directly proportional to the force. So as the force is applied, the resistance will change in proportional to that. So this type of tactile force sensors, they are used in robots, they are used in calculator keypads, etc. Now let's move on to this problem which says construct a force sensor with the following characteristics. Its range is given, which is 0 to 30 lb, and deformation it can have is 0.5 inches, which is the maximum deformation is given. Output is of 0.1 volts per lb, and a 1 kilo ohm linear motion pot is available with a 1 inch of stroke. So our goal is to construct a force sensor which should look something like this, and we need to calculate all the parameters which will be used in this. So first we have to find out the spring constant, and the spring constant we can find by using this range and the deformation which is written over here. So the spring constant, when you divide the range by this deformation, you will get 60 lb per inch, and that 60 lb per inch is the spring constant. And you can see the catalog for the spring constant, and you can select the material from there. Now next is we have to find out the voltage which it can have at a maximum load. So the desired sensitivity is given here, 0.1 volts per lb, and which dictates that the maximum output voltage will be 3 volts. So 3 volts we have found by multiplying this 0.1 sensitivity with our range, and in this range 30 lb is the maximum. So if you multiply it, then you will get 3 volts, and 3 volts is the maximum is the voltage at maximum load. Now next, the pot should output 3 volts when it is moved 0.5 inches, and you know that this is the maximum deformation we can have in our problem, 0.5 inches. Then next what we have to do is we have to find the pot supply voltage. So for that we will use the ratio. So we will use this ratio, 3 volts by 0.5 inches. 3 volts is the maximum output voltage we can have for maximum deformation, which is 0.5 inches. And in the ratio relationship, we will find out for 1 inches what will be the voltage for 1 inch. So the voltage will come out to be 6 volts. So the supply volt, that will be our supply volt. So if you put all these parameters into this diagram, then you will get the final circuit, and the final circuit will look like this, where this is the spring constant, and spring constant is 60 lb per inches, and the maximum deformation it can have is of 0.5 inches. So that's why the stroke has been given over here. And then we have this total pot in inches will be 1 inch, and we know that for that the supply voltage is 6 volts, which is mentioned over here, and the range is from 0 to 30 lb. So we already calculated that it is going to be 0 to 3 volts. 3 volts is the maximum voltage. So that's how you solve this problem. So this is the end of the lecture. Thank you so much for watching.